Well, hello and welcome again to our journey into complex analysis, and we're looking at section 4, which is the complex logarithm and complex powers. And we'll start with the complex logarithms. So we noted above that the complex exponential, which one can write as x, is not a one-to-one function. Indeed, it was periodic of period 2 pi I. And for that reason, it has no well-defined inverse. So we're in a sort of similar situation as you were with the sine and cosine functions back in the real world, where because they were periodic, they're not one-to-one, they do not have well-defined inverses. And so we had to do various things to try and get an inverse by restricting the domain of these functions. Anyway, solving x of w equals z is going to, for w, is going to produce, in fact, we'll see an infinite set of solutions, much the same as solving sine x as a half does back in the real world. And I'm going to denote this set of values by log z. This is small log of z. So when I write little log of z, I'm going to mean this complex, as we're going to call it, multi-valued set of values for the log of z. So formally, if we just play with the symbols, if I write x of w equals z, then I can write z in polar form as mod z e to the I arg z, where I'm taking here a general argument, not necessarily the principal one. And I can then simply formally think about taking logarithms of both sides, and using the ideas of log laws, I'm going to take ln mod z. Now mod z is real, so I'm going to write ln for the real logarithm that you know and love, plus I times arg z. Now arg of z, of course, is a family of numbers, and so we can define then. So that's what happens if I just play with the symbols. And now I'm going to, having seen that that's what it ought to be, then I'm going to define little log of z to be log of mod z plus I times the general argument, and that's going to be the principal argument, capital arg of z, plus 2k pi, where k is an integer. So that means the logarithm is an example of what we're going to call a multi-valued function. Now, of course, that's almost a contradiction in terms, because by definition functions are not multi-valued, but so the language is a little bit odd here, but that's the term, the name that's given here. It's a multi-valued function, and the important thing to remember is that it represents a set of numbers. It's often convenient to choose a branch of logarithm, and I'll say a bit more about branches in a moment. We're going to choose a branch of the logarithm to obtain a proper function in the usual sense. That is, I want to have a unique value for log of z, not infinitely many, and we want to therefore restrict the argument of the to be the principal argument. So if I restrict the argument to be the principal argument, then x of z is one-to-one mapping on c take away 0. Log of 0 doesn't have any meaning. And we obtain the principal logarithm, which I'm going to call capital Log of z. So capital Log is my principal logarithm, and it's defined for z not 0 by capital log of z is ln, real logarithm of the modulus of z, plus I times the principal argument. You could also write capital Log z of pb for principal value of little log z. We'll just do a couple of quick calculations for this. I'm going to find little log of z, capital log of z, for a couple of complex numbers. So firstly, of course, we'd like to know what the log of I is. So the modulus of I is 1, ln 1 is 0, and the principal argument of I is pi on 2. So the little log of I is I, pi on 2, plus 2k pi, where k is an integer. So we get a whole set of complex numbers here, and they're all purely imaginary. The principal logarithm of I, we simply put in k to be 0. We just take the principal argument of I, and it's just I pi on 2. which is rather nice. The log of I is I pi on 2. Now, in the real world you can't get the log of minus 1, but we can now. But the small log log of minus 1, the modulus of minus 1 is 1, ln1 0, principal argument is pi, and so we get the logarithm as I into pi plus 2k pi, where k is an integer. So again, the log of minus 1 is the set of numbers that are purely imaginary, and the principal logarithm of minus 1 is I pi, which again is quite nice. Just to do a slightly more general complex number, I've taken minus 2 minus 2i. Now minus 2 minus 2i lives about here, so minus 2 minus 2i. And you can see simple geometry shows you that the principal argument is minus 3 pi on 4. Now the modulus of minus 2 minus 2i is the square root of minus 2 squared plus minus 2 squared, which is given me 8, square root of 8. And the log of the square root of 8 I can write as a half log 8. Principal argument, as I mentioned, is minus 3 pi on 4, and then plus 2k pi, where k is an integer. And then the principal logarithm, then we simply put k to be 0 here, and I can write 8 as 2 cubed, so I can write the logarithm, the principal logarithm of minus 2i is 3 halves log 2 minus I times 3 pi on 4. Now, by the way, this business of taking the principal logarithm actually comes at quite a high price. And we'll see there are lots of prices to pay for this. It's a very expensive move. And the price we're going to pay for this at the moment is that we lose continuity and hence analyticity. So if it's not continuous, it can't be differentiable and it can't be analytic along the negative real axis. And just to give a quick hand-waving explanation of why this is so, if we look at, for example, if we take a complex number z up here in the second quadrant, and I'm going to imagine taking a limit as this z goes towards some number alpha here on the negative real axis. And I'm going to see what happens to the logarithm of z as my z moves down to here. Well, as it moves down to there, the principal argument is going to get closer and closer to pi. And so as z goes to alpha from the second quadrant, as in my picture here, then the log of z is going to go to the log of the modulus of z plus I times the argument, which is going closer and closer to pi. On the other hand, if I go towards this same complex number from the third quadrant, now of course the argument of alpha is pi, but in the limit, if I'm going this way, then we have to measure the angle in this direction, and the limit of the angle is going to minus pi. So the log of z, if I go from the third quadrant, the log of z is going to log of mod z minus I pi, and these of course are not the same. So that tells me if we take limits from two different directions, we get different answers. So the log is not continuous on the negative real axis. That's all the way across here. It's not continuous. It's not continuous along the negative real axis, and of course the logarithm of 0 is not defined. So that just gives a little hand-waving exercise as to why we've lost continuity and analyticity along the negative real axis. We also note that the log laws, here are our three basic log laws, they still hold, but only for capital log, in the sense that these are all sets. So this is a set of numbers, this is a set of numbers, so I'm thinking here of adding the values in the two sets together, and the sum of the values in this set plus the sum of the values in this set gives me a new set, and it does equal the same as log of zw, and the same for the rest. But they do not hold in general for capital log. So we've lost analyticity along the negative real axis, and we've lost, to our horror, the log laws. And let me just do an example of finding some complex numbers, z and w, just to convince you that in general log of zw does not equal the log of z plus the log of w. So I just picked a couple of complex numbers. I put z equal to I and w is equal to minus 1. And if I multiply z times w, then I get the log of minus I, and that's easy to show. That's equal to minus I pi on 2. Principal argument is minus pi on 2, and the modulus is 1. So there's the logarithm of the product. On the other hand, if I take the log of z plus the log of w, well, the log of I we've seen is I pi on 2, and we've seen that the log of w is I pi, that's the principal logarithm. Add these together, we get 3 pi on 2, and whoops, these are not the same. So this is different. So we've lost the log laws, and that's for the capital log log. So one has to be very careful dealing with capital log log. The rules of the game are not the same as they are in the real world. Also, if I want to find e to the log of 20i, well, what would you expect it to be? E to the log of 20i, you'd expect it to be 20i, and if you go back to the definition, that's exactly what it is. So that's perfectly good. On the other hand, the log of 20 of e to the 20i, you might hope that the answer is 20i, but it's not, because you've got to go back to the definition. So the log of 20i, the modulus is 1, so ln1 0, and at the moment this is e to the I theta, so the argument at the moment is theta, but that's not principal. So we have to subtract off 2 pi as often as we need to make sure that this here lies between minus pi and pi, that it's a principal argument. Well, pi is roughly 3, so if you think of pi as 3, this is 20 minus 18 is 2, and that lies between minus 3 and 3. So there's the value of the log of e to the 20i. So again, one must be very careful dealing with these principal logarithms. Little challenge problem here. You might like to see the connections between the inverse trig functions and the logs. So if we put w as inverse sine z, in other words we say z is sine w, then you're invited to show that the values of the inverse sine of z are given by this expression, minus I log brackets iz plus 1 minus z squared to the half. And of course one can do this by simply taking from this equation here, simply writing this in using exponentials, and you'll need to try and then solve for w, and when you solve for w you should find this comes out. You'll need to give a bit of thought to pluses and minuses here and give some thought to it. That's why it's a little challenge problem to do there. Now we can express the principal logarithm in polar coordinates by simply saying that log of z is ln r, where r is the modulus of z, plus I theta, where theta lies between minus pi and pi, and I'm going to make it strict inequality here, and r is positive. And again, I'm using ln to denote the real logarithm. Then the real part u is ln r, and the imaginary part is theta. And you can easily check that these satisfy the Cauchy-Riemann equations in polar coordinates that we saw earlier. And since the partial derivatives are continuous in the given domain, we can conclude that log is analytic in this domain. Now this of course excludes the negative real axis because we excluded both of these endpoints. However, everywhere else log is analytic, and we can use the formula for the derivative using the Cauchy-Riemann equations in polar form. We can do a little bit of simplification. We end up with this, and that's 1 over z. And so, as you'd expect, the derivative of log z is 1 over z, as you would expect. Now, there's a little challenge problem here, but I think I will actually do this one. It says, where is the function f of z log z minus z squared minus 1 analytic? I'll leave you to work out its derivative. As you would expect, its derivative should be 2z on z squared minus 1. I'll leave you to check that's right. But we just have a look at where it's analytic. So here's our function, log of z squared minus 1. I'm going to put z as x plus iy in. Now we've seen that f is not analytic. Well, firstly, it's not going to be analytic when this is 0, and that's going to happen at plus or minus I. And it's not going to be analytic when z squared minus 1 is real and negative. That is, when x plus iy all squared minus 1 is real and negative. If I expand this out, get the real and imaginary parts, so I get x squared minus y squared minus 1 is the real part of this when you expand it out, and 2xyi is the imaginary part, and we want this to be real and negative. Well, it's going to be real when the imaginary part is 0, and that's going to happen when y is 0, or when x is 0. So when y is 0, we can plug that into here. That'll give me x squared minus 1, and we want that to be negative. And that's easy to solve. You just get x between minus 1 and 1. Or when x is 0, that'll make the imaginary part 0. And when x is 0, you're going to get minus y squared minus 1, and that's automatically real and negative for any y. And so we can conclude then that this function log of z squared minus 1 is analytic everywhere except when x is 0, that's all along the y-axis, and when y is 0 and x is between minus 1 and 1. So that is between at minus 1 and 1, we've lost analyticity, and all the way in between. Apart from these two regions, then the function is going to be analytic everywhere else except there. So that's just a nice example of what we have to do when we're checking when this log function is analytic. And I'll finish off this section in another video.